Hello everyone. Ever wondered why a straw looks bent when you put it in a glass of water? That's refraction in action, light changing direction as it passes from air to water. Now, imagine that refraction happening at a curved surface like the edge of a glass lens or a water droplet. The way light bends at these spherical surfaces is what we'll explore today. And hey, here's a quick joke. Why did the ray of light break up with the mirror? Because it couldn't handle the reflection. Refraction at spherical surfaces means light rays bend when passing across curved boundaries between two different optical media, like air and glass, each having its own refractive index, which tells us how much light slows down. Speaking of which, the refractive index, or N, is the ratio of the speed of light in a vacuum divided by its speed in the medium. So, if light slows down a lot, the refractive index is higher. Now, to keep things neat, we use a sign convention. All distances are measured from the pole of the spherical surface. If you measure along the direction the light is coming from, that's positive. The opposite way is negative. The radius of curvature, r, tells us how curved the surface is. You can think of it as the radius of that imaginary sphere forming the curved surface. The key formula for refraction at a spherical surface is that the refractive index of the second medium divided by image distance, v, minus refractive index of the first medium divided by object distance, u, equals the difference in refractive indices divided by radius, r. Also, remember this. When light goes from a rarer medium like air into a denser medium like glass, it bends towards the normal line, and the other way around, from denser to rarer, it bends away from the normal. These everyday principles explain everything from swimming goggles to camera lenses. Let's dig a little deeper into how that refraction formula comes about. Picture a spherical surface with radius r separating two media, one with refractive index n1 and the other with refractive index n2. Imagine an object placed in the first medium at a distance u from the pole of the surface and producing an image at distance v in the second medium. Here's the neat part. Using simple geometry and a handy small angle approximation, which says that for very small angles, sine theta, tangent theta, and theta in radians are almost the same, we assign some approximate angles at points along the path of the light ray. The angles made at the object, the image, and the center of curvature can be expressed as small segments divided by their respective distances. Basically, we say angle AOP is roughly equal to height over object distance, h over u, and similarly, angle POP prime is h over v and angle COP is h over r. Next, applying Snell's law, which says refractive index times incident angle equals refractive index times refracted angle, leads us to relate u, v, and r. After substituting our angle expressions into Snell's law, we arrive beautifully at the formula we mentioned earlier. The refractive index of medium 2 divided by image distance minus refractive index of medium 1 divided by object distance equals the difference of refractive indices divided by radius r. This formula holds true particularly for paraxial rays, which means rays that are close to the principal axis and make small angles, so no wild zigzags here. This is also why optical surfaces need to be smooth and spherical for lenses to work properly, just like the ones in your glasses or camera. Now that we know how light bends at curved surfaces, let's see what kind of images form. Sometimes, the refracted rays actually meet at a point. When this happens, the image form is real and it appears on the side of the refracted light. Think of a magnifying glass focusing sunlight to burn a leaf. That bright spot is a real image. But other times, the rays don't meet after refraction but seem to be coming from a point when you trace them backward. That's a virtual image, like the reflection you see in a spoon. Your image isn't really there behind the surface, but it appears so. The nature of the image, whether it is real or virtual, upright or inverted, magnified or diminished, depends on the signs of object distance u, image distance v, and radius of curvature r. For instance, for a concave spherical surface facing the object, r is negative, and for a convex surface, it is positive. The magnification produced by refraction at a curved surface is given by the ratio of image height to object height, which turns out to be refractive index N1 times image distance V divided by refractive index N2 times object distance U. So magnification depends on both geometry and the optical properties of the media involved. What's fascinating is that these properties perfectly match what array diagrams show and what the mathematics predict, giving us a complete picture to understand lenses and curved surfaces around us. Here's where things get exciting. A lens is made up of not just one, but two spherical surfaces, each bending light. Imagine a biconvex lens. Light refracts at the first surface, then again at the second. When the lens is very thin, we can ignore its thickness, and by applying our refraction formula twice, once for each curved surface, we derive an important relationship called the lens maker's formula. For a lens placed in air, the formula to find its focal length f is that 1 over focal length equals the refractive index of the lens material minus 1 multiplied by 1 over radius of curvature of the first surface minus 1 over radius of curvature of the second surface. In simple words, the lens's ability to focus light depends on how curved its surfaces are and how much it refracts light compared to air. Depending on the signs and values of these curvatures, the lens can act either as a converging lens, focusing parallel rays to a point, or diverging, spreading rays apart. This formula is the cornerstone for designing everything from eyeglasses to giant telescope lenses. Next, let's talk about the famous lens formula that relates the object distance, image distance, and focal length 1 over image distance minus 1 over object distance equals 1 over focal length. Keep in mind the sign convention where all distances are measured from the optical center. Distances measured toward the incident light are negative and away from it are positive. This is the backbone of thin lens analysis, assuming the lens's thickness is negligible. The magnification of the lens, which tells how much larger or smaller the image is compared to the object, is the ratio of image height to object height, or simply image distance divided by object distance. When magnification is positive, the image is upright. When negative, it is inverted, just like turning a photo upside down on your phone. This lens formula doesn't just pop out of nowhere. It's derived by combining the two refraction equations for spherical surfaces, making it an elegant result from fundamental principles. Here is another example to solidify the lens maker's formula. Suppose a biconvex lens has refractive index 1.5, radius of curvature of the first surface plus 20 cm and the second surface minus 20 cm. Our goal is to find its focal length. The lens maker's formula states that 1 over focal length equals the lens's refractive index minus 1 multiplied by 1 over radius 1 minus 1 over radius 2. Plug in the values. 1.5 minus 1 times 1 over 20 minus negative 1 over 20 equals 0.5 times 2 over 20, which is 1 over 20. So the reciprocal of focal length is 1 over 20, meaning the focal length f is positive 20 centimeters. A positive focal length confirms this lens is converging, bringing light rays together, just like your reading glasses. Knowing this formula helps lens makers create precise lenses for cameras, microscopes, and more. Now, special cases make life simpler. For a plano-convex lens, where one side is flat, so radius of curvature on that side is infinity, The lens maker's formula simplifies to 1 over focal length equals refractive index minus 1 times 1 over radius of the curved surface. Think of it as a single curved surface lens with one flat side. For the equiconvex lens, where the radii of curvature are equal but opposite in sign, radius 1 equals negative radius 2, the formula shows 1 over focal length equals 2 times refractive index minus 1 times 1 over radius. This symmetry doubles the effect of one curved surface. Of course, these formulas assume thin lenses. For thicker lenses, we need to consider the thickness and how the optical center shifts. And don't forget, choosing the right signs for radii is crucial. Getting a plus or minus wrong can radically change focal length calculations. So, always keep your sign conventions sharp. To wrap up, we have a few key formulas to remember. The refraction at a spherical surface formula states that refractive index of the second medium divided by image distance minus refractive index of the first medium divided by object distance equals the difference of refractive indices divided by radius of curvature. The lens formula relates image and object distances to focal length as 1 over image distance minus 1 over object distance equals 1 over focal length. And the lens maker's formula connects the focal length to the lens's refractive index and curvatures as 1 over focal length equals refractive index minus 1 times 1 over radius 1 minus 1 over radius 2. Magnification can be found using either the more general formula involving refractive indices and distances or simply image distance over object distance for thin lenses. All these principles come from Snell's law and the geometry of spheres, and they form the foundation of optical instruments like microscopes and telescopes, tools that help us see the very small and the very far. Sign conventions and paraxial approximations ensure our calculations stay accurate, making physics not just theory but a practical guide to the world of light. That's it for today's journey into refraction on spherical surfaces and lenses. Remember, physics is as fun as it is fascinating, especially when you can bend light and your mind at the same time. See you in the next lesson.